All right, so we are working on hypothesis tests. We're going to go to the StatKey data sets. So I have those under useful websites, or you can go to StatKey to get them. And textbook data sets here. And again, these are also available. Oops, that's not the one I wanted. I wanted the Google version. Wrong button. Google Drive, there we go. And the one I want to look at is called HeatCognition. HeatCognition, where are you? HeatCognition. Let me go by it. Oops, I went by it. A, B, C, D, E, F, G. It's not in here. What? Okay, so we're going to go a different way. We're going to go to StatKey. And at the title here from StatKey, we're going to go to their datasets page. It must be a newer dataset than when I downloaded them. 3rd edition. Okay, it's got to be in here. HeatCognition, there it is. And then what happens if I click the CSV one? It wants to download it. What if I do just the text one? I just want to copy it in the StatKey. HeatCognition text. Ah, there we go. Okay. Can I just copy this? And oh, it's going to want to copy. Oh, shit. What did I do? All right. All right. I guess I need the spreadsheet version. So let's go back, try that again, because I don't want all those columns in StatKey. That'll confuse StatKey. All right. So HeatCognition, open up the spreadsheet version. There you are. And then we are just going to copy a column here. But first, we got to look up what the data means. So mine's throwing it into Excel. So here's the Excel. So I have AC, yes or no. I have math, ZRT, and then color ZRT. So we're going to use the AC and the math. So we're going to copy those first 2 columns from the spreadsheet. And in a minute, we'll paste it in the StatKey. Before we can do that, we need to read what the heck does all this mean. So documentation for the data sets is down here at the bottom. And I want to find the one called HeatCognition, because if we don't know this, we can't do anything. All right, HeatCognition. Let's blow this up a little bit. 46 college students were asked to solve cognition problems first thing in the morning during a heat wave in their northeastern city. 20 of the students had air conditioning in the rooms and 26 did not. All right, Z-scores of reaction times are given for the math problems. Okay, so, you know, some people were quicker than others, so they recorded the time to perform these skills. Anybody remember what a Z-score is? Way back from chapter 2? A Z-score measures how many standard deviations is your score from average, right? So they looked at how long it took all of them to do the math test part, and they found the average. And then for each person, they calculated the Z-score, which was how many standard deviations from average were they, okay? So that's what they're using for the measurement here. And either they were below average or they were above average, according to the standard deviation. All right. I think that's all we need to know. All right, so the catch here is we have essentially kind of 2 samples in one, because we have a qualitative variable and a quantitative variable. So we have students, we're just going to call it the student's math score. And we have 2 groups of students. We have with AC and without. So with AC, and we have without AC. And these are measurable numbers, and with measurable numbers, we can find averages. So we're going to find some averages here. So we're going to find the average math score for the people that had AC. So maybe I'll call those average with a little AC down there. And then we're also going to have a sample average for the people that did not have AC. So maybe I'll put a no for them. And we're wondering is, if it's a heat wave and you have to think really hard, does having AC or sweating your butt off matter? Will they have different averages, or will the averages be about the same? Right. So whenever we're comparing two averages like this, the default assumption is it doesn't matter whether you have AC or not. There's no difference. That's the null hypothesis. So whenever you're comparing, so with a comparison, the null hypothesis is that there's no difference. So it's going to take a little bit for us to think through what our hypotheses are before we can use StatKey here. Okay, so no difference. Well, that means I'm subtracting them, right? So maybe I'll take the average of the AC people minus the average of the no people. And the null hypothesis is that we expect that to be about 0. That's the null hypothesis. Except I have one small problem. I can't call that the null hypothesis yet. There's something wrong with my symbols. Somebody asked a question about this in the beginning of class. A null hypothesis always has to refer to the population, not the sample. So what symbol should I use instead of X bar? I should use mu. Yeah, so to make this a formal hypothesis, I have to say mu AC minus mu no AC. We expect that to be 0. So that right there is my null hypothesis. H, that's supposed to be an H, 0, colon. Sometimes what we do to make this a little less to write, I just want to look at the difference in those means. So I might say mu diff is 0 is another way to state that. Is the difference in their mean 0 or not? Now, there's some evidence that a little bit of stress can make people think better. Too much stress, however, can make your mind kind of fall apart, right? So is the heat a little stress that might make them think better, or might it be too much stress and make them not think as well? That's a tough one. So I don't know, right? I might say, well, I think AC actually is going to be better, but I don't like being cold personally. If it's too cold, that's worse for me. I'd rather be a little warm. So so I'm going to go for a conservative alternative hypothesis, and I'm going to say, I don't know which way it's going to go. So I'm just going to go for a not equal. So that's going to be my alternative. So I'm going to say the alternative hypothesis is that that difference in their means, I'm going to call mu diff, is not 0. Now, somebody else might argue otherwise. They might say, no, I'm sure AC is going to make a difference and their math scores are going to be better. Okay, so if that was the case, I'd have to rethink what that would mean. So I'm going to make some notes here on that. So what if somebody said mu AC is going to be greater than the mu for the no AC people? Was anybody thinking that here? That the people with the AC are going to do better on the math test? Yeah, right. So that's what you're thinking. So to turn this into a alternative hypothesis, I got to get the mu's on the other side. And I'd have to keep the same order. So I did AC minus no. So I'm going to subtract the no's to the other side. So that would be mu AC minus mu no would be greater than 0. Or I could say the difference in the means, mu diff, is greater than 0. So there's a couple of options here. A lot of people would say, this is what I think is going to happen. I think the AC people are going to do better, which means, are they going to do a right tail test or a left tail test? Is this a right tail test or a left tail test? It is a right tail. Greater than's right tail. Yeah, greater than's to the right. So this would be a right tail test. So if that was your alternative hypothesis, and this is a possible alternative hypothesis here, you would do a right tail test. I'm going with the conservative one based on the fact that I don't like being cold. I'd rather be a little warm. I think I'll be just fine. Could I be wrong? Sure, I could totally be wrong. And besides, I want to go over what a two-tailed test is like. Then a right tail isn't much different from the left. You just look on the right side. Okay, so we're not going to do that alternative. We're going to go with this alternative here, which implies I have a two-tail test. All right, now we got to go to StatKey and figure out where the heck do we put this data to get the right sampling distribution. All right, over to StatKey we go. Okay, Am I doing descriptive statistics, confidence interval, or a hypothesis test? I'm doing a hypothesis test, right? Okay, so then am I doing a single mean, a proportion, a difference in means, a difference in proportions, or am I playing with slope? This is a difference in means, yeah. Okay, now the difference in means isn't always that. So in this case, right, I have two different groups of humans that I'm comparing. That's definitely a difference in means. However, there's another study you'll read about in the book where students took their pulse rate during class, and then they took their pulse rate while they were taking a quiz. Two different sets of data, but those data are paired together, and that wouldn't be a difference in means in that case. Okay, that would be a single mean, and I'll talk more about that later. But whenever you have what looks like two different means, you got to ask yourself, is the data paired or not? This data ain't paired. Some people were in the AC and totally different people were in the heat. Not the same person in both places, okay? So yeah, difference in means, that's the right place here. And then we edit the data, delete whatever's there, paste in what we got, and hope StatKey likes it. Let's see, do I have a header row? I did bring in the header row, and StatKey says it likes it. Cool. All right, next. Before we had to set the null hypothesis at the top, what does this say? It says mu1 equals mu2. Oh, so I went, yeah, so I went, let's see, I downloaded that data, it ended up in Excel, and I copied columns A and B. Yeah, with when you have two different groups, you need the categorical variable in StatKey along with the numerical variable lined up like that. Yep. Another question?
I don't have Excel downloaded.
Okay.
And it doesn't let you download it into your office.
Okay. All right, let me get you that data set. Let's see. Oh yeah, I could share it with you. Okay. Let's see. Oh, I could put it in here. All right. So if you had any trouble, then what I'm going to do is in this Google Drive data sets, where'd it go? I'm just going to upload that file that I didn't have there before. Upload HeatCognition. Okay, so now if you go to the Google data drive, Google sets, it's in there now. Sorry about that. All right, so then if you copied it in there like I did, then what you should see is that N1 is 20. So whatever set 1 is, there were 20 of those, and whatever set 2 is, there were 26 of those. So if I look back at the data set description, it said 20 students had AC. So they're calling data set 1 the AC people, and data set 2 the no AC people. So I'm going to put that in my notes too, because StatKey is writing it different than I did. So they're calling it, like in this line here, let's use a different color. They're calling it mu1 is the same as the mu AC, and mu2 is the no AC. And again, there's two ways to look at this. If you subtract them and set it equal to 0, the difference is 0, there is no difference. If there's no difference, then they're also equal. So we could also say mu1 equals mu2, right? Those are two different ways of saying no difference. Right? And I like to go with the difference is 0. StatKey likes to write it as they are just equal. So see up here, they put mu1 equals mu2. So that right there means no difference. So there's two ways to think about that. And I mentioned at the beginning of this exercise, this is about the hardest problem we could possibly look at. So it doesn't get any harder than this throughout the rest of the quarter. So if we survive this, we'll survive the class. All right, guess what we got to do next? Generate thousands of samples based on this one. All right, I got 6,000. Now, looking back at my notes, I got to remember, which kind of test am I doing? I went with there is a difference. Could go either way. So that's a two-tail test. So next I select two-tail. Okay, now StatKey randomly puts 95 in the middle, 2.5% in each tail, and it marks lines at the bottom to say, okay, these are what the difference in means would be on either extreme end. If your data set falls in between, that's pretty typical based on a sample like this. If your data falls in the red region, that's atypical. This is with a 5% significance level. We have to split the 5% into the tails. So StatKey picks, in this case, 5% significance level. Last time it picked a 2.5% significance level. We changed that. What's the mean for our sample, mean difference in our sample? It's negative 0.01 or negative 0.1, sorry, negative 0.1 is the difference. And is that in the red region or the black region of this graph? It's in the black region. Okay, so what that means is negative 0.1 is close enough to saying they're the same. Okay, so does having AC matter for your ability to do math? The answer is not based on this sample. We fail to reject the null hypothesis. We have to, the data supports the null hypothesis. Negative 0.1 is close enough to 0 in the difference in their performance, the difference in the time they took to take the math test. Now, we also should calculate the p-value. We haven't done that. All we did is look at the graph and say, right, the mean up here, x bar 1 minus x bar 2, the difference in our sample means is negative 0.01. That falls down here on the graph, which is in the black region, which means it's close enough to what I was thinking, which would be no difference. All right, so to calculate the p-value, we go and replace one of those numbers with our number from the sample. Well, it's a negative number, so it better go on the left. Don't put it on the right. That would, weird shit will happen. So I just go down here to this negative number at the bottom, and I type my sample difference, negative 0.1. I hit enter, and StatKey recalculates both sides for me. For a two-tailed test, the p-value is both numbers by the red region combined. So on the left side, I've got 23.9%. On the right side, I got 23.9%. So the p-value is the sum of those two numbers. And we're going to write down what that means next. So make your best sketch of this on paper.
Can you do that one more time?
Yes, the whole thing?
Just like so where it got shorter and like
Yes.
the red is up higher.
Yeah, okay, so I'm just going to turn that off there. Okay, so once I generated my thousands of samples and I decide I'm doing a two-tail test, I just click two-tail. And the computer usually throws a 95% in the middle. What I want to do next is to take my sample value right here. And that goes on the bottom axis. Since it's a negative number, it's got to go on the left side. So I just take this bottom left number, click on it, and I replace it with the number from the original sample, negative 0.1, and click OK. And then StatKey recalculates. All right, so then do my best sketch of this situation. New page. So this is performance on math test. And we had mu AC equals mu no AC. And then just like always, I draw my best bell-shaped curve. I like to make a mark down the middle. So if they're equal, that means if you subtract one to the other side, then the population parameter is 0, right? That was the other way I wrote it. So 0 goes in the middle. And then StatKey helps us figure out what the scale is down here. And so my sample value, my X bar diff, I'll call it, ended up being negative 0.1. That ends up being around here. Since this is a two-tailed test, I have to reflect it over to the other side. Now, theoretically, it would be the same, but positive 0.1. StatKey called it positive 0.095, which is similar to 0.1. So I'm just going to call this one about 0.1. And then I do my shading, left tail, shading for the right tail, because this is a two-tail test. And StatKey gave me on this side point, what was it, 239? 0.239, yep. And a matching 0.239 on this side. Remember my alternative hypothesis, HA, was that mu AC was just not equal to, that's why we did a two-tail test. So to get the p-value here, I have to add up those two numbers. So the p-value in this case isn't just the left or the right, it's both of them. So 0.239 plus 0.239, what does that give us? 8, 7, 4, 0.487. As a percentage, I can call that 48% chance, 47.8% chance. 48.7% chance of what? What does a p-value mean? So the p-value is the probability of finding another sample like this with either a lower average difference or a higher average difference when we expected there to be no difference. It's a conditional probability. The expectation was we expect no difference. This is the chance of finding another sample that is much lower than -0.1 or much higher than +0.1 for the difference in the standard deviations of those students. All right, 48% is way bigger than 5%, right? This is much bigger than 5%. 5% is the standard significance level. Standard significance level. So you only get to reject the null, which we're usually excited to do. Wow, look at the research says, hey, this is some new information. Is this new? Nah, this says there's no difference. Sorry, this is about the same as, 0. So in this case, we fail to reject the null. So that's my decision. Decision, fail to reject null hypothesis. No. So here's the reason we don't say we accept the null hypothesis. This is just one sample. It may be a good sample. It may be a great representative sample. It may be the best work we've ever done in the world, but there's always a chance we could make a mistake. We never know 100%, so we can never say something is true. We can just say the data supports it. So that goes into my conclusion. In my conclusion, I'm not going to say I accept that there's always going to be no difference. All I can say is this sample supports that there is no difference in performance, whether there was AC or not during a heat wave. Right, so that's what I'm going to state next. And again, because we don't have all the data, we didn't do every college student ever at every heat wave, right? All we can say is it supports the data. We don't know for sure, but it leans toward, doesn't matter whether you get AC or not, you're still going to do just as well on the math test. Now, okay, never mind, that was a silly idea. I was just thinking of other distracting things when you're trying to take a test. Someone's calling you, you got kids around, you got to pee, you get the sniffles, right? There's all kinds of things we can measure. All right, so that's the decision. Let's write a conclusion, and then we're going to say what the p-value means. And the p-value is the harder one. So what is our conclusion? Remember, conclusion is a press release. Okay, let's see. So I got to go back and think about this. We fail to reject. That means the data supports the null, and the null hypothesis says there is no difference in performance. Okay, so whenever I do one of these, I always have to kind of play around and write notes about what the heck I'm talking about. What's the population? What's the alternative really mean to my mom? What does the null mean in just plain English? Because if you don't have that, there's no way you can write a conclusion. All right, so I think I got it down. Let's see, the data supports supports. Sometimes we put supports the claim, lots of ways to say it, that there is no difference in this case in performance. Am I misspelling performance? Is it preformance or PER-formance? I got it right? Oh, good, thank you. No difference in performance on a math test, or they were doing math problems, but similar, close enough, during a heat wave with or without AC. And that's my first draft. So then I reread it. Does it make sense? Would my mom ask me questions about that? Yeah, so in this case, instead of putting that the difference is 0, I think people would like the phrase no difference instead, right? So I'm just kind of thinking like press release and my mom. Yeah, I think that's a pretty good conclusion there. That probably, so the question was, would I want to specify that the different groups of conclusions? That probably would make a better sentence. It would be twice as long, but better. Yeah, and sometimes, and we'll look at some other examples later, you do have to be that specific for other people to get it. So instead, how would we rephrase that here? Let's see, that there is no difference in performance on a mass test during a heat wave where some students had AC during the test and some didn't, right? So yeah. So next we need to go over to the English department and help us revise this after. So but that might be better. So where had AC, I probably should write air conditioning because some people won't know the phrase AC, and some did not. While taking the test. Every once in a while, I do submit some of these to the English department and say, okay, do you get what I'm saying here? Could I word it better? And we argue about it. Let's see, while taking the math test. Yeah, and it's always hard to figure out how do you best write it so it's not too long and you get the point. And that's why up front, right, you got to say, do I know the population? Do I know what each group is? Write it down. It's worth writing it down to get it set in your head. All right, here's the harder part. Now, so anytime you do one of these, what I expect you to do is I expect you to be able to calculate a p-value for me, use the p-value to say whether you're going to reject the null or fail to reject, and then look back at what the whole problem means and tell me what the heck, how do you explain this to my mom? Okay, so if you can do all that, you're going to get an A. If you want an A+, you're going to tell me what a p-value means. So let's look at what a p-value means. So the p-value is a conditional probability. Oops, wrong button. And we'll stop after this. Get out a little early today. All right, what does a p-value mean? In particular, we're going to go over what does this p-value mean? So in general, a p-value is the probability of finding another similar sample with more extreme results when you expect whatever the null hypothesis said is going to happen. So in this case, it would be the probability, there we go, of finding another sample with a difference in means that is less than. So if we were just doing the left tail test, we would just say less than that negative 0.1, less than negative 0.1. But since this is a right tail, I got to go look at the right side. So then I would say or greater than. I got to describe those two red tails. And I'm just going to round the right tail cutoff to be positive 0.1, since 0 is in the middle. When we expected a mean difference of what? 0. Yep. Yeah, so under the condition that we expected the difference to be 0, what's the chance another sample would be way to the left or way to the right of what our sample was? And again, we have to reflect to the other side. StatKey does that automatically for us. We don't have to worry about it. It just says, hey, this is about what the other side would be, which is super nice. If 0 is not in the middle, that reflection is trickier, right? So mostly we won't do that. Mostly we'll just put 0 in the middle. And this is about the hardest kind of problem we'll look at. Two different groups at the same time. We look at the difference in their means. StatKey does most of the work. The hard part is setting it up and interpreting it. Okay. All right. I'm going to stop here, and then we're going to do more of this stuff tomorrow.